Thanks, Joel. Hi, everyone. So my name is Judah, like Joel said. And let me just say a mini spiel, since this is supposed to be a learning environment. If you want to like talk to me about something that I say, or you have a question about it, it's the generic thing where you're supposed to speak up. But I'm a pretty friendly guy, and if you say something like, that's not right, like I know for sure because I work on that, then I have the ego to take it, and I'll be able to talk to you about it. It's okay. So you can bring things up. I also know I have, my buddy pointed out that I possibly have a lot of slides. I'm not going to burn through these. We're going to get through whatever we can get through, and maybe we'll get through the end of like some part of this and you can get some closure to some of the idea, but if not, at least we'll like learn some math along the way maybe, or get some ideas, and that'll be enough. And then tomorrow, so we're going to see the same slides basically 3 times. So today you'll see this set of slides. Tomorrow it's almost an identical set of slides, but with code inserted, so that you can you can see what the code for the theory looks like right next to it. And then the activity is basically the slides, and you're going to try to create the things that we've talked about as much as we get through. So, yeah. You have anything you want to say right off the bat?
Let's get started.
All right, great. Thanks, Eric. Okay, so I also was told, I guess you guys got a lot of different backgrounds. So I'm a lattice field theorist, as Joel said, so I worked on a bunch of toy models most of my life. And so the partition function is the thing you're interested in. Maybe in your field you're not particularly interested in the partition function, but that's what I'm mostly going to talk about. I guess this could apply anytime you're summing over a lot of local degrees of freedom, or you have many-body physics, or many bodies, or few body even. This could work out. So computing the partition function is a very difficult problem. And it'd be nice, or even to get log of the partition function, so a free energy type thing would be great. And this, you can't do this. This is, it's a huge number for anything that matters. It's completely useless. So it's also if you're more of like a particle field theorist, and you're like, why is he talking about stat mech? If this wasn't made clear in earlier lectures, the partition function is the path. So Feynman's path integral is in Euclidean space is a partition function. And so all your favorite things about stat mech, or the things you are afraid of, unfortunately, they're the most important aspects of quantum field theory. And so it's important to calculate these partition functions and understand that thing. I know I'm supposed to talk about tensors, but unfortunately the optimum solution to these types of problems is usually Monte Carlo. So Monte Carlo is spectacular. It's basically been the backbone of any actual physics that's been done in the past 40 or 50 years. And so it's extremely important to understand, or these Markov chain methods. But in low dimensions and for some problems, the Tensor Renormalization group is excellent. So Monte Carlo has some issues. I'm just going to enumerate some of them. There are a lot of interesting problems. Unfortunately, it's usually the actual problems we want to solve that have to do with real life. There's this thing called the sign problem. So you might have seen in your Monte Carlo stuff, you have this accept reject thing where you have a probability. And sometimes that probability is negative, and so like negative 80% is like doesn't make any sense. Sometimes it's complex. That also doesn't make any sense. And so and that shows up in interesting cases. It also only until recently have we been able to do very large volumes for physical systems, and that's because it has a big problem. When you're taking something to the 4th power and you add a few lattice sites, it gets bad real fast. And another horrible thing is also usually in the most interesting regime. So you're usually near these critical points or phase transition points, and that's precisely where the algorithms, a lot of them perform the worst. And so the most interesting part of the phase diagram and the actual physics, the part where you can start extracting some continuum limit normal quantum field theory information, is also precisely the region where the algorithm slows down and does the worst. Okay, so the Tensor Renormalization group. How am I doing? Too fast?
Just slow down.
Yeah? Okay. I just don't want to like catch people off guard here with the, okay. tensor renormalization group, it doesn't have any of these problems. There's some pathological situations where maybe it might have a sign problem, but it doesn't really have a sign problem. And that's because it doesn't sample. So there's no probabilistic aspect to this. So if you don't like the whole probability side of Monte Carlo, you're gonna like this because it's not even there. It scales great with the volume. If it takes you about an hour, so it scales linearly in the number of iterations in time. And so if it takes an hour to do one iteration, to do 30 iterations, it takes 30 hours. And each iteration is a factor of 2 lattice size. So if it takes 5 hours to get a 32 size lattice, to go up to 64, it's 1 more hour. And then 128 is 1 more hour. And so you can get, 2 to the 32 size lattices or whatever in 2 days. If it takes an hour, for instance. And since it doesn't have this probabilistic aspect, it doesn't slow down. It doesn't slow down for any region of the phase diagram. It's the same speed in all the phase diagram. So it's got a lot of great things. So this scaling with volume is the time. It has its own problems, but and the reason it's not the cure-all to everything. But I want you to know it solves these because I want you to be impressed by this. Okay, so let's talk about what the renormalization group is. So some intuition about why the algorithm looks the way it does. Okay, and I'm going to put this in words too. In this tiny picture, I'm doing like both at the same time. In this tiny picture, you've got these pixels. And the intuition this is supposed to build is that at very small distance scales, so I'm talking about real life here, at very small distance scales, you've got things like blipping in and out of existence, things are interacting, it's nuts, and the rules are somewhat goofy. So we've invented this, quantum field theory to describe this stuff. And so you've got these tiny microscopic degrees of freedom, and they have very interesting rules, and they're somewhat non-intuitive. And as you zoom out, you stop seeing these tiny microscopic structures of the physics, and you start seeing kind of these emergent structures. So like you start seeing large scale things as you get further and further, and the microscopic and the rules don't seem to be applying as much either. And then when you zoom out enough, you can't even see the microscopic details anymore. And instead, these kind of large scale structures have their own interaction rules. This is the reason why when if you took Physics 101 and you learned about projectile motion, you didn't need the quantum theory of gravity to understand why you throw a ball through the air and it arcs in a parabola. It's because there's effective theories at every scale. So as you zoom out, you don't need quantum rules to describe classical things. And that zooming out process, that's called the renormalization group in some sense. So, yeah.
Just clarifying, so you're saying like, when you're looking at one energy regime, you only need to look at quarks and gluons. But if you're like
that's right.
at, something a different energy scale, you don't really care about what the quarks and gluons are doing. You care about what the protons and neutrons are doing with each other instead.
That's exactly right. And I've got a slide dedicated to that. Yeah. So Eric said at larger, like in QCD, at larger scales, you don't need to see quarks and gluons. You can describe the whole theory in terms of nucleons. And there is an effective theory for nucleons, and you never need to mention the smaller things, and that's exactly right. So here it is written out. We have rules that govern short distance, high energy interactions. And the thing is that those rules actually don't efficiently, they do it correctly, but they don't, for our little brains, they don't efficiently describe the large distance physics. So you could try to do like, atomic interactions with like full-fledged QCD with quarks and gluons and stuff, but it would be nuts. And so, but it would be right, but it's a waste of time. And so the renormalization group is it's a mathematical framework that lets you, it tells you how the rules change with length scale. And it gives you, it generically, Kenneth Wilson and Leo Kadanoff, they sketched out these generic rules about how to do this, about how to make the rules change with length scale. What am I doing here? This isn't too bad, it could be worse. Okay, here it is said again. With the example, I had a slide for this and we got to it a little sooner, that's fine. So you want to, now there's math words showing up and the math is, so you want to integrate out or sum over the short distance physics or the high energy physics. So what that means is you want to incorporate, you want to take into account the configurations, or the way your quantum field theory looks, or the way your model looks at short distances or high energies. You want to take those into account when you describe the long distance stuff. So these things act some way at this tiny thing, and you want to include all the ways they do that when you build this larger theory. So you get a new theory at a larger length scale, but it actually has all this tiny stuff included. You've taken all those configurations into account, and the way you do that is you sum over slices in this partition function. But we'll get to it. And you get some new theory with like nucleons instead of quarks and gluons. Is it somewhat in your bones, a little more than it ever was? Let's just say that, like a finite amount more. Anyone want to say anything about this?
You briefly just mentioned slices of partition function. You mean you're taking like the high energy part and taking some of it and integrating that apart?
Exactly. That's exactly what I mean. Yeah. So in the partition function, you sum over all the configurations of your spins, for instance, and yeah, what I was mentioning is that you sum over only the high energy configurations, for instance, or yeah. Okay. Tensors has to work its way in somehow, so let's do it. So this is what we're going to do. We've got some tiny intuition about what the renormalization group is. Now we need to start talking about tensors. And I got to be honest, this is going to be the driest part. So if you're like checking out hard this morning, I mean, I'm trying to keep it active, but there's going to be math, so we're going to have to deal with that together, and like we can talk about it all the while because I'm here for you, and I want to be so. I'm serious. I want to I'm not trying to exclude people by writing fancy or like math or put symbols. I'm just
before we go to the text.
Yeah.
This renormalization group, is it like an actual group?
No.
Okay.
Great question. Why would it even be called the renormalization group? For anyone who wants to get like mega nerdy, I think it's a monoid or a semi-group with identity, or yeah. And so if you wanted to investigate what it is, no kidding. So
Could you put whatever those math terms were in like somewhat layman terms?
Yeah, the reason is you can't. Well, we're going to get to it. More stuff will be uncovered, but when you do this sum over high energy configurations or short distance physics, you actually lose all the information. So you can't invert renormalization group transformations. So there's not inverse transformations. So one way is to say is like uncovering where this like large distance physics came from. There isn't some like unique path to get back down to the high energy scale. It gets blurred out, and you can't see what it is anymore, and that's why it's not a group. Okay, so we're gonna look at a really simple model. Who here? Does anyone here? And this, don't worry if you haven't. Has anyone seen the Ising model? Who here's seen the Ising model? Sometimes called the Ising model. Great. This isn't the gauge one. This is the spin model. So Ising spin. Great. It seems like a lot of people have. If you haven't, we're going to review it. So we're going to construct our model in terms of local tensors, and the partition function's going to tell us how to contract or sum over these tensor indices. And this is going to be the hardest part and what we'll focus most of the time on. And then you want to do this over and over again and hopefully find something interesting. Okay. So we're going to start at 1 now. There's not going to be coding aspect. I mean, you can try to like write this in real time as I'm like lecturing, but I would recommend pencil and paper or pen and paper. Okay. So this is the action for the Ising model. This is like inverse temperature or coupling, and then here are the spins. And so they only take 2 values, +1 or -1. And so the action's hilarious because it's just like 1 + 1 + 1 -1 -1 + 1 -1. It's just some string of pluses and minuses of the number 1 multiplied by a number, but it for some reason it's remarkably interesting. So it looks like this, maybe graphically. So down spin, up spin, and this interaction is just the multiplication of the nearest neighbors. That's what this notation means. So this is like -1, -1, +1, -1, and so on and so forth. Here's the full partition function. So this fancy notation means sum over all possible spin configurations. So what that means is in here you could have like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, -1, 1, 1, 1, 1, 1, 1, 1, -1, -1, and all the ways you could fit in -1s and +1s. You have to sum over all of those. This summation symbol here, it's inside an exponential. Nothing's quantum here. This is classical statistical mechanics. That's the beauty of quantum field theory, is that it's classical in one, instead of 3 + 1, it's classical in 4 dimensions, if they're Euclidean. And so these are just commuting variables. The sum comes down, everything's fine, and it's a product of exponentials. What we want to do is write the partition function as a trace or a sum over all tensor indices. So we're going to figure out what this is. We don't know what it is yet. And there's going to be a ton of them. They're all identical. It's the exact same tensor over and over and over again in some huge product. And their indices are just tied together. There's like, an infinite number of sums trapped in this little trace symbol. But we're just summing over all the indices of these tensors.
So are we ignoring the observable tensor?
No, everything's included. This is, so, I see, it's my bad. It's not a matrix trace. So this isn't a trace over like, that's right. So when you normally think of a trace, you think of I sum over the diagonal elements. In this case, I just wanted to try to capture that there's a lot of indices here, and every single one of them is summed over. Not,
It was one-dimensional, it would be matrices in normal trace.
That's right. If it was a 0 + 1, so it would be a trace. Yep. All right. Excellent questions. You guys are doing great with questions. Okay, this is just like from like what's this like experience. This is just because I've done this a lot. I'm trying to, for 1, 2, and 3 here are just going to be like words of wisdom to people if they ever want to get into this when forming. So this isn't necessarily part of learning it, but it would help you in the future. When you try to write one, you want to try to figure out how to write a tensor that only involves pairwise contractions. So you don't want 4 things being summed on the same index. Like you guys might have seen, I want to use this once, like, you don't want like, this looks dumb. Like, we don't want situations like this. We want situations where it's just pairwise. So I want like alpha, beta, and then gamma, say gamma here or something. I only want the same thing to show up twice. This is typical in like Einstein summation convention stuff, is you normally only want the index to show up twice. But computer scientists, for instance, they don't care. Like you'll see code written, and it'll be in some of our stuff where you sum over the same index multiple times. But for peace of mind, it's good to try to make it this way. All right. Everything's got to be discrete. There won't be any integrals in the tensor formulations. Just 0, 1, 2, 3 discrete numbers. And for the most part, real life is very like translationally invariant. So physics right here usually looks the same as physics right here, and so on and so forth. I mean, you get charges involved and things start to be weird, but for the most part, for free theories especially, it's basically the same everywhere. And so we're going to find, when we write a tensor, it's going to represent everywhere. Like that tensor is going to be true throughout all of space-time. All right, it's happening. So let's go through this. Okay, there's the way we're doing this, I'm going to show you 2 ways to make a tensor network, and there's probably more than that. It's not unique. So we're just going to go through 2 ways. Okay, this thing from before, this is called the Boltzmann weight. This thing from before, if you think of these sigmas actually as labeling the rows and columns of a matrix, this looks like a matrix. So if this is like up, up, it's this one, up, down, it's this one, down, up, it's this one, down, down, it's this one. And so you can think of these as actually the indices on a matrix. And by taking their 2 different values, it labels the 2 rows and columns of this matrix. Okay? Why does that matter? This is involved in 4 different terms. So that matrix shows up, for instance, here, 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 and here. Remember how I said we don't want that? So we need to find a way to make it so, because this variable is interacting with this one, with this one, with this one, and with this one. And so in this matrix, this matrix shows up, or well, this index shows up the same in 4 different matrices. We got to get rid of that somehow, just to make things easy on us. So here it is. This is something you can do with any matrix. It's called the singular value decomposition. It doesn't matter what matrix we're talking about. And so it lets you kind of turn a matrix into, they're not always the same one, but it kind of lets you write a matrix as a product of 2 smaller matrices. So this thing can factorize into a rotation matrix, a diagonal matrix, so this is the same matrix multiplied by itself, and it's diagonal, and then another rotation matrix. And lambda's diagonal, and the entries are always positive. The important thing is that you can always do this, and you can always clump them like this. Because lambda is diagonal, and it's positive, you can always take the square root. And so every matrix in the universe can be written as a product of 2 matrices that are built out of a rotation and a diagonal, and the same diagonal and a different possibly rotation. It just turns out in this model, because this matrix is really pretty, that these are actually the same matrix multiplied. So this is like a matrix square root in this case. Yeah.
If you can do this, doesn't that mean that it should be positive semi-definite or?
That's right. If you can take, that's right. That's exactly right. If you can do square root of a matrix, it means it has a Cholesky decomposition, so it has to be positive semi-definite. I'm pretty sure that's true.
Is it always the case?
What is? Sorry.
Is M always positive semi-definite?
This matrix will always have this form. Yep. Okay, so now we did it. I don't know if you're like, so it's all by itself now. This thing is no longer coupled to any other spin variable. We've introduced this like virtual intermediate index but it's coupling, this like intermediate index is the one that's coupling to the other spin, but it's not the other spin. And so now wherever this whole thing shows up 4 times, I can take this one all 4 times from its 4 little pairs, and now I can get rid of that sum. So somewhere in here is the sum over that particular local variable, and I can do it, and I can do it for every single one on the lattice now. So there it is, and somewhere else there's this one too. There's like so many of these. There's like as many sites as there are. There's that many 4 clusters of sums. But we can do them all because this matrix doesn't have the other summation variable in it. It's somewhere else. We've like factorized the spin variables into 2 separate matrices. And so now I can do all the sigma sums, and I've just been left over with these new alpha sums. So these aren't gone, that's for sure, but all the sigma sums are gone. And so this is a tensor formulation for the Ising model. So this is the same local tensor everywhere in space. It looks the same for every single spin, and it has whatever form these W's have, like that. Any part about that, hit me. I'm ready.
Wait, so you said you don't want to have like you have that spin variable repeated 4 times sigma I.
Yeah, this is the 4 times,
Okay. So you don't want.
but it's nowhere else.
Okay.
You do it once with null.
Yep, and this doesn't show up anywhere else in the partition function.
Okay.
This is some other spin, and it shows up 4 times over here somewhere, and I do that some too, to be sure, but they all look just like this everywhere.
After the indices, 1/2 on the matrix of lambda, there was the value 1/2.
This is yeah, it's a good question. This is what I mean. So it looks like these are the entries, and it's diagonal, and so all I'm doing is, and there'll be 2 of them. And now this product is the original. Exactly. You can only do that because it's diagonal. I mean, specifically. Okay.
Can I do this if your Hamiltonian has like interaction between 3 spins, or is it just this method only one?
Yeah, more complicated ones are possible. This type of, so this is why I'm showing 2 approaches. I'm about to show an approach where you can do something like that. Yeah. This type of one is special. Mm-hmm.
And what kind of schemes do these work for? Do they work for anything that you can represent as +1 and -1?
Yeah, I think you could like Zn or like Zn models, I could imagine.
Isospin?
Like isospins. Yeah. I mean, I wouldn't do it this way.
Okay.
I do it the way I'm about to show.
Okay.
I guess that didn't answer your question, but let me think about it.
I'll see, yeah.
Okay, here's the other way. I'm like getting really excited. Okay. No one else is, but I'm like jacked about this. So, all right, the other thing you can do is, you might have seen that like Euler identity where the e to the I theta is like cosine sine. This is the rotated version of that. And so it's cosh now, and there's no I, and it's sinh, and the sigmas are right there multiplying it. Here's a compact version of the way to write this. You have some coefficient, so it's cosh or sinh. So if n is 0, it's cosh. If n is 1, it's sinh. And then, when this is raised to the 0 power, there's nothing there. And when this is raised to the 1 power, there it is. And so this is this expression. And this achieved exactly what we wanted to do the last time. We wanted to get these things all by themselves. So I didn't have to move the sigma I and sigma j together everywhere we went. Everything's commuting. It's all classical. And so this thing is free to, it can move out. I mean, I can move the sum over and it can move willy-nilly around. Same with the sigma j. And so here, I've also figured out a way to factorize the spin variables. They're not in like a matrix anymore. They're not the indices, but they're out and about and free again. All right, what about this first line? Yep.
Doesn't this identity depend on the fact that you need to have sigma I squared is 1?
Doesn't this identity? I don't think so.
Maybe not. I'm just.
I don't think so. I mean, it depends on you can invert this relation, and you have to be able to invert this to solve for the coefficients. That's all I can think of. Say it one more time.
So here, the sigma need not be like the Pauli matrices. It could be.
No, that's right. They are not the Pauli matrices here. These are classical fields, and they just take the value 1 and -1. I'm not doing anything in quantum here.
Oh, okay.
This is the 1 plus 1 dimensional quantum Ising model, but it's the 2 Euclidean classical Ising model, which is the same model. Okay, first line good. Second line, do that thing. So get this all by itself. So everything that you don't want to use, it's fine. Just shove it all the way over there on the line. You want to get this sigma with the other 4 sigmas, the other same 3 other same sigmas that are also somewhere in this line. So move all the sums over to the left, move all the c's over to the left, and get that same sigma together. It shows up 4 times because there's still 4 nearest neighbor pairs, and so you get them all together. It's a number, so it's some number to the n power, and you're summing over the values that number can take. I guess I'm not giving this side like any attention whatsoever. I don't know why I'm I'm excited about that side. So you're summing over this plus minus 1 still, and these are from the 4 nearest neighbor pairs. And you can see when you do that, you're going to have 1 to a power plus minus 1 to a power. The only way that's ever going to pan out is if the sum of that thing is 0 or even. So if this sum is negative, if the sum is odd, 1 plus minus 1 is 0. And then the whole partition function is 0. And so the only way you get a non-zero partition function is if the sum of these n's that you expanded is an even number. And so these are 0 and 1. So only 16 possibilities. No, it was my fault.
Delta mod 2.
Delta mod 2, thank you. So the sum of these has to be even. So 0 mod 2, or mod 2 equals 0. And this is now our tensor. So here's the thing we just found. So these 4 n variables have to be even. These c's are the quotient cinch from before, and they're shared between 2 different spins. So this c sub n, it actually knows about this one and this one. It's the same n in this case. And so I have to share it between 2 different spins. And so it's square rooted. So the product will give me a full Cn. And so this is the alternate tensor. And so for people that asked, this is generically called like this is like a version of the Fourier expansion for discrete things. Also called the character expansion. And so here we've expanded in terms of group characters. The group is trivial, it's 1 and minus 1, but we've expanded in terms of the characters of the group. And it looks like this. And you can do that for many other groups, and it generalizes like 3 body interactions, other type of things.
That tensor doesn't necessarily have to be right.
It doesn't have to be real. It is in this case. It's just coches and cinches. So they're all positive too. I mean, unless you move to like negative temperatures or stuff like that.
The new tensor that we just built, does it replace our partition function?
So the partition function now, okay, so each one of these is an index. It has the value 0 or 1, and the partition function now looks like this. So there's it's like can we all get on board that what I use for an index doesn't matter? Yeah. Is that okay? So it's like, and then somewhere down the line, beta shows up one other time, and then somewhere down the line, A shows up again for some reason. Maybe it has alpha too, and it's just like, and then all these things are summed over. So there's a ton of summations here too. So it's still a partition function.
Yes, it's helpful when you put the tensors on the nodes of the diagram and you can like your fractions have to do with the legs.
Diagrammatic notation is about to be inbound, so let's make sure we understand this. All right. Okay, so here's the tensor, and now we're gonna start drawing pictures because it makes, instead of writing these t's and the summation symbols and all this crazy stuff, you can just start drawing pictures, which is really nice. So here the ends correspond to different legs, so the different indices correspond to different legs of these tensor crosses. And so, for instance, when I have this, so they can only take 0 and 1. When this one's, what do I have here? When this one's 1 and this one's 1, and these are 0, 0. For instance, the tensor, I tried to make it look like 0, 0, 1, 1. And so this would be cosh-sinh, and it would be non-zero, or this would be okay. This one's also another valid thing. All of them, 0 is valid, and all of them 1 is also valid. And so this is kind of a first step in diagramming these tensors. They got to be even because of this Kronecker delta. In the other one, that thing doesn't crop up so easily. But yeah. So this is actually a theory of. So I thought, okay. Let me just tell you this quick. I thought about, if someone wants to do this, I thought about making this a game, because there's only like 8 or 16 of these pictures you can make, and it's like a theory of closed loops. So you find out that because of this rule and the evenness thing, you only ever have intersecting or closed loops. And so I was thinking, like, you could make just like 8 tiles, and you could have to like tile the board, and you'd want to close as many loops as possible, and you get points based on that. Or maybe like you could adjust, maybe temperature could be involved somehow, but there's only like so many, there's like a finite number of vertices here because of this, and you could imagine placing those little tiles next to each other so that the little black ends here are always touching. And so that's what this theory looks like, just so you know. Okay, here's some more diagrammatic notation. So if you put 2 t's together, so here I'm summing over a single index that I've called alpha. All the unsummed ones are free indices, so they're not connected together. And this would be a 6-index tensor, 1, 2, 3, 4, 5, 6, and there they are. And so diagrammatically, you don't have to write this every time. You can, or even these, you can just do this, and you know it's the same tensor because we wrote it so it's exact same tensor everywhere. And so when you put 2 tensors together and you contract them, you know it's this tensor. Also, you can do like traces over indices over the same on the same tensor. So for instance, if I, what did I say here? If I glue the horizontal ones together, that's like this. And if I glue the vertical ones together, if I contract those, that's me doing this. And so this is a number. So there are no free indices here. So it's not a vector or matrix or anything. This is just some number. And this is a much larger tensor than this one originally was. So this is a much larger array, and this is just a scalar number. And these pictures show that because there's no open dangling legs. Okay.
The second that one corresponds to the function.
Oh, I'm sorry. These are not necessarily related to our model. I was just showing that this is like just a diagrammatic technique. I guess if you had a single site on your lattice, this is the partition function. If you had a single site with periodic boundary conditions, this is Z in that case. And yeah, it's all right, great. So this is the answer. Here it is. This is the partition function. If you could somehow do this, you'd have Z. So these are all tensors. If you could glue them and you loop this for periodic boundary conditions, say you contract the opposite edges together, or open boundary conditions, or whatever you call it in your field, where there's nothing here and they don't touch back again. And this is Z. You can imagine why this is so difficult now. There's tons of contractions here, and this could be a very, very large number because there's so many terms in the sum. But take note that if you've done this somewhere, you've done it at all the other blocks in there. So that if I do this sum, that's the same as doing this sum and this sum and this sum and this sum. And so when you do a block, it's the same for everywhere else in the lattice. And so just focus, I don't have to necessarily do all those sums. I can keep using the piece I've already made. So if I could do this, for instance, then I don't have to make another one. This one is the same as this one, and so I can just put it with itself over again. I don't have to store so many different tensors in memory, for instance. Okay. Okay. How does the renormalization group fit back in this? Good job, Judah. Way to put this back in. Okay. So we've seen the tensors, and we've taken a model. We've reported the entire partition function in terms of these local tensors. How does that somehow relate to the renormalization group? So let's say we put a block together. So this is short distance physics. It's on the order of the lattice spacing. It's actually the shortest possible distance you could explore. So this is our short distance physics. We've taken 4 tensors. We've contracted them in a block, the tiniest kind of cluster we could make. And it's now an 8-index tensor, sure enough. You can think of these as 4 much larger indices. So instead of 2 values, this takes 4. So each one of these takes 2 values for the Ising model, but then their product state would take 4 states, for instance. So here we've contracted for them. This is a sum here. There's a bunch of sums. And it's a new theory. So this isn't a theory of if you look at the microscopic details, it's a theory of intersecting loops. But if you look at this new tensor, there's 4 states instead of 2. So it doesn't look like it's the Ising model right away. There isn't that simple even Kronecker delta thing. And it's because the inside of the blocks are summed over. So what goes in doesn't have to come out in that Kronecker delta way. There's actually many ways that the interior could happen. Has anyone done Feynman diagrams? Happen to have done some Feynman diagrams? So this is exactly what happens in Feynman diagrams, is you have incoming momenta, but what happens in here is unknown. You can't particularly see what goes on in there. And it's because we've summed over all possible configurations inside here. So, these could have the black lines going in, but then it's maybe all these go out, or maybe it just does a loop, and it's not clear. And you've taken all that into account when you've summed over. And so you've summed over the short distance details, and you have a new theory with a new tensor, and that tensor describes seemingly a 4-state model that was not what you started with new interactions between them. And that's part of the renormalization group. It's good to kind of see that. I've said this, I guess I was really excited about how expensive this operation is. Oh, look, this is a cute thing. You don't always see this. This is how expensive it grows. So each index, the number of states you have to keep on the nth iteration goes like this. So it's gigantic, huh? It's exponential. And so you can only actually contract some of these tensors exactly. So now let's get to the algorithm. How are we doing? Everyone okay?
Yeah, Judah could just slow down.
Okay.
Yeah. So I just clarify one thing you said to go from 2-state model to 4-state model, because these pairs, like 0, 0, 1, 0, 0, 1, and 1, 1 on the pairs of legs coming out of the new tensor block.
Yep. That's exactly right.
And then if you do that again, it's just bigger and bigger.
It's a 16-state model. It's because here's another fun thing, and this is if you're not sold on the lattice, or maybe you're a diehard anti-lattice person. Here's something cool you can't avoid. This Ising model it's the same as scalar field theory in the continuum. So having +1s and -1s on a little lattice, when you do the renormalization group procedure, this has the exact same propagators, the same correlation functions as scalar field theory and 1 + 1 phi-4 theory. And so it has the same critical indices. It is. And that aspect of these numbers of states proliferating, so yes, it starts as 2, and then when you get a new tensor, you get 4 and 16. It's because this thing's trying to and capture an entire real field that runs from over all numbers. And so if you could have an infinite number of these together, you'd rebuild, and if you tuned to the critical point and took the lattice space into 0, you'd rebuild 5-4 theory in 1 + 1. And that's what it's trying to do. I said this. Okay. Approximation schemes. This is like what we're going to code tomorrow, and look at. Okay, people have invented a ton of approximation schemes because you can't do the blocks very much. The most famous and original and inspired one is called the Tensor Renormalization group, TRG. One that came shortly after that's been very successful in higher dimensions is the higher order tensor renormalization group. This list is going to get nuts. There's tensor network renormalization. This was made by fancy people at Perimeter Institute. And there's loop tensor network renormalization, which is an improvement over this somewhat, or a different take on it. Both of these use the idea of entanglement entropy to coarse grain. So it looks at entanglement between blocks and attempts to remove how much information one knows about the other. There's another one called graph-independent local truncations tensor network renormalization. This one I think was invented by I heard a bunch of grad students who thought they could do a better job than all these previous ones, and it does pretty well. And there's a lot, and they're all different approximations and attempts to make that block of 4 as best you can. We're going to do the simplest possible one, which is this first one here. And if we have time, we might look at this one. Okay, so we can't do the block. So the block, there were 2 legs coming out each side here. What if instead we use that singular value decomposition to generate a virtual index inside here? And then, so we'll just have 1 thing coming off here instead of 2. So we're still going to try to do this interior block, but instead of dealing with these sets of 2 indices, we're going to have this virtual index, and we're going to control how many states are on that virtual index. So here's a dumb way of doing this. If these each had 1 state, this would be a number. So that's very easy for a computer to store. If they each have 2 states, now it's 16 numbers, but you can see if you control how many possible values the tensor indices take on these virtual legs, you control the amount of memory you're using and how demanding the computation is. And that's what we're going to take. That's what we're going to take advantage of. So we're going to generate these virtual indices, and we're going to control how much information is stored in the virtual indices.
So what you're saying is instead of going like you're taking a block,
yep,
and then take another block, and another block, and then you're connecting.
Yeah.
Okay.
Yeah, so down here is another block. There's another square right here, another square right here, another square right here, another square right here. But we only need to do it at one place because it's the same everywhere.
Yeah. So is the new vertex that you're generating the same copy of does it have the same state? If this is +1, should that also be +1, or is it not necessary?
Say it one more time, I'm sorry.
So it's like, you have blocks adjacent to each other. What you're basically doing here, you're moving the blocks by creating 4 virtual edges. So the 2 points connecting the virtual edges, should they have the same state, like +1 and +1? Yeah.
No. So that's a great question, and let's talk about it. The states are associated with the legs. So the spins are gone now, we integrated them out. Instead there's like n's or whatever I call them, ijk here. So this could be like 1 and 1, so there's an even thing. This virtual index will demand that since this was even, whatever happens over here also has to be, has to fit in that scheme. It's got to be even. You can't just have like a single leg. But it doesn't have to match what these ones are, for instance. Does that answer your question?
No, I was looking at the fundamental picture, right? Like, I'm still thinking of each vertex having like ±1.
It's gone.
It's gone. So
we did that summation. I mean, it's that interpretation is no longer.
But
we can't
it
get
can still be mapped to that one, right?
Yeah, but doing the SVD, I mean, there's no SVD on those. I mean, maybe you, I mean, I'll say it. Maybe you like see something that I can't see, but I don't know how to do it. It's not clear to me how to do that. Okay.
So in this picture on the left, you're just basically pulling the tensor apart, putting kind of a virtual.
I'm going to show you right now. It's this. So I took the two indices, and they have geometric analogs. So the two indices that in my mind correspond to the left tensor leg and the top tensor leg, I make them into a single product state. So there's 4 states here. So this has 2 values, this has 2 values, and it's all their possible values. And then I take the right and bottom tensor indices that correspond to the right and bottom geometrically. I make a new state. So now this is a matrix. This is a 2 by 2 by 2 by 2. It's got this 4 by 4 has all the same information. I've just done np.reshape in 4, 4 to this thing, and it makes this. And so I've got a matrix now, and then like Joel said, this splitting of this tensor, I do the singular value decomposition. So every matrix I can write as a unitary matrix, a diagonal positive matrix, and another unitary matrix. This is diagonal and positive, so I'll break it in 2. And I've got 2 matrices here. They do not have to be the same, for instance. So I kept them generic. And so these 2 matrices, this is matrix multiplication over alpha. But these i's, this capital I was a product state. And you could reopen it back up. You could do np.reshape on this I and make it, instead of 4, you could do 2, 2 again. And so this is 2 3-index tensors that are now summed over this intermediate index here. Great.
And why are we doing this again?
Yeah. We're doing it because we're going to change the number of states stored in here so that this doesn't grow out of control. So instead of, if we kept them all, it would just get larger and larger. Instead, we're going to say, maybe we can just drop some of these inside here, and that'll control the computation. Yeah, so you guys are asking like questions, and the slides are kind of trying to get there. So it looks like we didn't buy ourselves anything. So this is, the size of this alpha index is 4, and it has to be because we did a decomposition of a 4 by 4 matrix, and so the intermediate virtual index still has to have the same size, and so it actually looks like we didn't gain anything by doing this. But we can drop some of these alpha states. The singular values of this matrix, you can organize them from largest to smallest, and the smallest ones contribute least to the norm of the matrix. And so this is a way of approximating, by dropping some of these, you can approximate this T matrix as best as possible, and by that I mean the tensor norm is preserved as best as possible. So if you multiplied this bad boy by its complex conjugate and traced over, you did that with this approximate one, where you've dropped some of the alphas, you'd get as close as you could to that number, that norm value. And so instead of keeping all 4, which doesn't gain us anything, we can drop down to some smaller number, 3 or 2. I mean, you don't have to do it at 4. You can go, when your computer gets too large, you can start dropping then, or when the memory gets, starts being a problem for memory, then you can do it. But that's the plan.
What makes some of the singular values small now?
What makes some of them smaller?
Yeah, well, you did singular value compositions before.
Yeah.
Now you're using the fact that some of them might be small, you can drop them, the norm's the same.
Absolutely.
Why use that now? Why you not use that before? What makes them smaller now is my question.
Oh, I see. Some of them have always been smaller.
Yeah.
But when we were, you mean when we were making, when we were doing the tensor formulation to start?
Yeah, this isn't your first singular value composition.
That's right.
Now you're using what singular value composition does.
Yeah.
Just drop them. I'm wondering why now and not before.
So it's a good question. For formulating this tensor, we lucked out because the tensor actually only does have 2 states. And so the fundamental tensor, when we were making those W's, there's no way the 2 by 2 matrix is going to have trouble for the computer. So we don't need to truncate at that point. In fact, I mean, you don't have to truncate at this point. This isn't very demanding. Like a vector of 4 is not like huge, but it's the spirit is that when this virtual index gets too large, when you've contracted too many tensors, this is the point at which you cut during this singular value decomposition.
So can you also do the previous step first, then you have a 4x4 matrices, then do the...
Exactly. Yep. That's common. Okay, we'll talk more about this tomorrow when we try not to do things in a bad way on computers, but contracting this way is a poor idea. So there's 4 free indices and 4 summed over. So this is a number of states to the 8th operation. So, if you're a computer science person, you're like, it's polynomial, who cares? But it's a horrible polynomial. It's to the 8th. And so it's very expensive. 2, yeah, maybe it's not too bad. 2 to the 8th, your computer's probably fine. But when you've got 100 states on each leg, it's brutal. This is much better. There's 1, 2, 3, 4 free indices and a single sum. This is a d to the 5th, or number of states to the 5th operation. And so it's 3 less than 8, so it's better. And so you want to do smart contractions when you put these. So you could just make the block, right? This is what we were trying to do. That's what I'm trying to say. Let me get back to it. Sorry. This is what you want to make, and you could you've done it. Like you've got this thing here. You've done this. It's the P. You could just put 4p or 2p's and 2q's together, and you could straight up make this. You could do np.einsum, or you could do 8 for loops, and you could make this block, and you've done a coarse graining step. This is inefficient. Try to do something like this, but we'll talk more about it. So you do top and bottom. You put p and q together, and then this is pretty cheap. This is pretty cheap. And then you put these 2 together, so there's only 2 sums here, because these have already been done. And so now it's 1, 2, 3, 4, 5, 6. And that's the most expensive part of this. So the ultimate cost for doing the TRG is number of states to the 6th operation. What do you guys think about these diagrams? Did I get into diagrams too quickly? You guys want to talk more about them?
I am really curious what you drew these diagrams with. Are they ticks?
Great. It's in MetaPost. Something called MetaPost. Great question. I have questions like that all the time too. I see some slides, I see talks, and people have some incredible graphics, and I'm like, how did you do that? All right.
So after you do this blocking, like where you form these bigger and bigger blocks, if you look at the effective theory, like would it have like so in terms of these new degrees of freedom or whatever, so would it have like higher order terms from the functional theory, or?
Yeah, so it's a deep question. So it's good. There's arguments among TRG practitioners about how much of an actual renormalization group transformation this whole procedure is. So like some of the perimeter people, the reason they went with this entanglement renormalization group stuff, or this loop TNR stuff, is they're convinced that the TRG and HOUTRG are not genuine renormalization group transformations. And so they've invented these other algorithms that they feel are more in the spirit of renormalization group. Let me answer your question. There are certainly higher order things generated in this. Whether or not you're flowing in a Wilsonian, like nice RG way towards the actual fixed point, it's not clear. I mean, it's probably not is actually the answer. I mean, it's probably not real RG in the way we'd like it to be. Yeah. But there's higher body interactions and stuff generated. Yeah. Okay, so this new tensor looks like this. It's got 4 legs. The lattice has now been turned crooked, and we'll deal with that in the same way we got to this point here. Let's go over what we did. So go back.
Should I look at this like on diagrams like you made an effective vertex of some more complicated?
You know, it's kind of feels like that, yeah. I think that's safe. It is not like I would not say it's a Feynman diagram because it's completely non-perturbative.
No,
but
I'm not saying it's
like
that
it.
spirit.
Yeah.
It's affected.
It seems to look like it a lot, yeah. Uh-huh.
So there's no problem with that, right? The periodic boundary condition should also somewhat change.
Yep. So like there's a bunch of squares, and when you get to the end, some of those squares wrap with the ones at the top. Absolutely. When you're at this point, the lattice has become goofy. So let's turn it back to a square lattice after we talk about this. So you have to do this. You have to make an initial tensor. To make the first block, you do this SVD on the top corners to separate out the corners, and then you put the corners together in a block. If you need to, you can truncate in that virtual index, and then you end up with some weird, goofy sideways tensor that looks like this. So it's not the original lattice yet, but we'll get there. Okay. Yeah. Did anyone see that, like, maybe we were, from this point, we were just going to tear this thing left and right and do SVD again, because that's exactly what we're going to do. So we have this awkward-looking kind of crooked tensor. We're going to reorganize the indices and separate the left and right pieces and make a matrix again. And we're going to do SVD on that matrix. Instead of writing this, here's what it looks like actually. So here's that 4-index tensor. We make a product state, so it's a matrix. We do the SVD over this intermediate virtual index, and we make another block out of these 4 sideways ones. Now we're back to the original lattice. So this is actually, at this point, you've completed 1 full block of the lattice, and you're back to a lattice with double the lattice spacing here.
Maybe this is it's still a square lattice.
This is a square lattice.
No, 4. It's just
Yeah, it's just turned sideways. It's root 2 length, the lattice spacing.
okay, that's it.
Now it's double. Now you've put like a block together.
So your first step, the index we call alpha, for the first SVD, it can have 4 states. Now you're going to put something that would have 16 states, correct?
If you didn't truncate at all.
You don't truncate at all. Correct.
Yeah, that's right. Yep.
The next step would be 16 times 16, 256. That's all.
Yeah, it would be awful. I agree. Okay. It does get awful. Okay. That's it. That's the algorithm. So, I mean, we're gonna have to spend more time tomorrow. I'm like up for it, but I'd like you to do this later tomorrow, or the thing I'm going to try to talk about right now. So, any other aspects about this you guys want to go over? I'm down for anything. We can talk about it anymore. Tomorrow I'll show some code snippets about how to do these parts. So, and maybe once you see that, seeing more in practice stuff is sometimes easier. Yeah.
So if I wanted to read more about this, make in preparation for the activities, or if you have any suggestions of where I might go, or what resources I might,
I'll put them in the activity folder tonight. That's a great idea.
You can put your slides in there too.
Sure, I can put the slides in there too. Yeah.
Okay, so this is coming from somebody completely new to this subject, so I'm sorry if I offend you. But it seems like you've done a lot of work just to get a square, and I'm not really sure what the point of that square is.
Yeah, you're totally right. I mean, it's 100% right. So, yeah, I mean, I guess I'll briefly review, I'll say the advantages again. Because you want to make like in the way you said it, you want to make like the largest, most beautiful square you can. And this is what it looks like. This is the answer to all your problems. You take the log of this and you take derivatives, or you do other things with this, and you can understand your model in its entirety. So the goal, in some sense, is to make a giant bunch of squares. This is also a square or this is also like a cross tensor. If you think this is one state, so this times this times this times this times this is some huge product state, this is some huge product state, this is some huge product state. And so this is a 4-index tensor. It's also a cross, and it's made out of these little squares. And so the advantage of this is computing these squares once you really get in there and you get you've got your BLAS and LAPACK and you've got your fast libraries working. Building this square can take, I don't know, 1 second, and it'll take days for Monte Carlo people. I mean, it's a factor of 10,000 speed up or something sometimes. It's nuts. So I talk to like Monte Carlo people, and I'll show them a plot of all these data points, and they're like, wow, that's wonderful. The agreement's great. Like, how long did you take? It'd be like, I did this in the time we were talking. I'm dead serious, in like 2 seconds. And they have to run on overnight or something. And so it's great. And so the reason you got to work on this algorithm, and it's true, the cost, it's painful to write this stuff, but the benefit for, at least right now, 1 + 1 and 2 + 1 dimensional systems is it's the speed, man. It's nuts. Does that kind of help a little bit?
So basically you're making this type of grid every time, but the grid is different based off the model, right?
Yes. It's completely model specific, absolutely. Yep. Yeah.
So is this method restricted to, I already said you only have finite dimension of your perspective?
No. So no, but for computer's sake, you have to truncate the local, yeah.
And also, can you generalize this to 3 dimensions?
Yep. Yep.
So, so you've done these blocks, you've gotten the tensors, you've done the truncations, you've done a few iterations of this. Now, how do you get, say, specific heat so I can see a peak and find the critical temperature?
Yeah. You know what I might do? So I only put one slide in about that, and it's because I didn't know what people would care about. I will make 2 more slides about that. I can show you what I've got right now, but you're not going to be happy at all. I mean, basically, as you build these blocks, if you don't renormalize, the number just gets huge. So even if I'm truncating, if I don't normalize this thing by something, so I'm still adding a bunch of numbers, and as I keep doing it, it'll overflow still very quickly. So you have to normalize this. And so if you save those normalizations, like if you save the log of the normalizations, you can reconstruct log z from those normalizations pretty simply. It's later. I'll add some stuff.
Also, if you want to calculate the correlation of 2 spins, let me do that.
Yeah. Advanced questions. Okay, awesome. Well, so what ends up happening is not this one. Yeah, he asked, how do you do spin-spin correlation functions, correlation functions? What you end up having are at the locations where there are where the spin is. So if I have a spin here and a spin here, these tensors are ever so slightly modified usually. So instead of the Kronecker delta even rule, it's usually odd. So what goes in doesn't have to be what comes out, and it's because there's a source there. So instead of black line comes in, black line goes out, it's usually just black line leaves, and these are all empty, and it's because it's generating flux, and then that has to end somewhere that also is like that. Exactly. It's usually something like that. All right. I know I said I wasn't, and I won't if you stop me, but I am gonna try to, I do wanna try to get through this since everyone seems on board. Here's a slight improvement. So this is the next level. This one also tries to approximate the norm of the tensor as best as possible through an SVD-esque thing. And so it's not, this doesn't use some deep insight. It's based on SVD kind of again. But it does a little better, usually. Okay. This is half of a block. You guys have been great, by the way. I know, like, it's dry. It's just a bunch of pictures and math. And I get it. Thank you. So here's half of a block. So instead of trying to make the block, we're actually going to start at this level of approximating already this piece here. And it does well, nevertheless. So when you just put two tensors together and made this 6-index one, so we have this M, and you could, for instance, lump these together and make it another 4-index. We want to try to make a tensor that has approximately the same norm as this tensor. Okay, how we go about that? First, if you were to compute the norm, it would basically look like this. So you'd take an M and an M star, and if you wanted the actual number, you'd sum all the indices together with their corresponding partners. So for instance, the trace of this matrix is the norm of M. Everyone see that? If not, I don't mind going in greater detail. So to get the norm of something, you multiply it by its complex conjugate, and you sum over all the indices in the same location. And that's good for any array. If we leave two of them open, like I have here, the trace of this thing is the norm. So to approximate the norm of this, we want to maximize the trace of this matrix. This is something that is complex conjugate, so it's positive definite. And because of that, if you were to look at the eigenvalues, if you just keep the largest eigenvalues, you're doing the best you can at approximating that trace, because they're all positive. And so if I keep the largest eigenvalues of Q, I'm getting as close as I can to approximating the norm of M.
Sure.
Yeah.
Eigenvalues, are they going to drop? Are they going to be like a very quick, rapid drop off? Is it going to be like step function? It's going to be
You're all asking excellent questions. It's clear why you are all here, and you're all going to be wonderful physicists, every single one of you. It's great. So what's going on here is the eigenvalues for this operation and the TRG, and this is what motivated people to invent this like huge list of algorithms, is when you get near like critical points, these eigenvalues don't drop off necessarily so quickly. So it's not, you usually end up sometimes having to cut right in the middle of like a bunch of large eigenvalues, and that's not a good cut. And so people have tried to figure out ways around that. So if you're far from criticality, if you're deep in either phase, yeah, I think, and there's some physics to that, right? When you get near critical stuff, correlation lengths are going nuts. It's not clear what matters. Okay. Here's Q. This is the eigen decomposition of a generic matrix. In this case, Q is Hermitian, and so it's our unitary diagonal and the same unitary. These are the eigenvalues.
So is there a kind of slowing down then?
It's not a slowing down, but it's a loss of info, yeah.
Because you have to take higher number of states, and so it does kind of slow down the method.
Yeah, sure. I see what you mean. Yeah. I mean, the loop TNR people, they keep 6 states through criticality, and it does great. That's why they've invented these improvements. But yeah, this particular one has that form of critical slowing down. Sure. Okay. So this is the eigen decomposition. It looks kind of like the SVD. These aren't the singular values, but they're close. We just want to keep the largest of D But we're not gonna, so before we like lumped the eigenvalues and the unitary matrices together, we're not doing that in this one. Instead, we're just gonna keep, these i's are the rows, we're just gonna keep alpha columns that correspond to the largest eigenvalues. So the truncation is gonna come in the column of how many columns of this U matrix we actually keep. So let me just say this again. So each row of U, or each column is a eigenvector, and alpha enumerates the different eigenvectors. The D's, and so they match with their corresponding eigenvalue. We want to keep the eigenvectors that correspond to the largest eigenvalues. And the reason we want to do that is we're going to rotate this M by applying these U's onto it. So we found this U for this I index. This is precisely the index we isolated before. And so we found the U, so the eigenvectors, and it's a rotation matrix, it's unitary, it's orthogonal. And we're gonna apply it to the M indices, and we're gonna rotate it into the largest eigenvalue basis. So, like it's, right now, the M indices all the values are there, and they're in some basis. These U's they're gonna try to put it right at the largest, so everything lines up at the largest eigenvalues for the ones we kept. And then we're throwing away the smallest ones. And you have to do that. I mean, life goes on. So that's what we're doing. So it's not worried about the actual eigenvalues. We're just changing this tensor actually by rotating the basis so that when you take the norm, it's as close as possible to the original M.
So it's kind of similar in spirit to physical component analysis.
Yeah.
Finding the subspace.
Yeah, I see what you mean. And this is the new 4-index tensor, 1, 2, 3, 4. And so you've put two of these together, you've approximated half of a block. So you didn't do the full block, but that's fine. If you don't make any truncations whatsoever, you'll notice when you put two of the, so if this is the full U's, they're unitary, so when you put two U's together, it's just the identity. And so when I put imagine this, the copy of this, I put it in here and I'm plugging it in, so these two U's connect. If I didn't truncate any states, it's U times U dagger. And so it creates the full block unadulterated if I don't truncate at all. If you do truncate, it's an approximation of the identity in between. You can do this in one direction, and it's instead of making blocks, you're making a transfer matrix, for instance. So you could put this with a bunch of its buddies and make the partition function that way. Or you can make a block and put it with the other half. That's all I got. That's all I want to go through. Anything else anyone wants to talk about? Anything at all. It can be just like physics stuff.
So, what's the scale of these TRG as opposed to like the full fledged? You're like, we're 1, 2 to the 2 to the end.
Yeah, that's what it was.
Yeah. How does this truncation change that scale?
It will be, when you get to the value, it's fixed at that. So if you want to keep 40 states, once you get to the number at or greater than 40, you truncate back down to 40, and it's 40 from then on out. So there's no more scaling at that point. Yeah.
So after you do this you do a truncation and then you do plotting and you keep iterating as possible.
Exactly.
So if you don't do this truncation, is this transformation invertible? Like, can you go back to the original?
I don't think so. I don't think so because when you do this sum, there might be special cases, but when you do, for instance, this sum, it's hard to see that from staring at the elements of this tensor. Yeah, I don't think so. it's some like, it's like some differentiation thing or something. I don't know. I don't think it exists. I mean, you're asking like wonderful, like abstract questions, and I'm on board, but I just don't think, I mean, like I said, specific cases, if you stare at it, you might be like, I can see this is like the product of two things, but I don't think it's invertible in general.
So this seems like a very powerful method, but why it doesn't replace the Monte Carlo? What's the restriction of this method?
It's too expensive in 4 dimensions right now. So I've done 3-dimensional stuff, 2 plus 1, I mean, and it's doing okay. In 1 plus 1, if you can do this for your 1 plus 1 dimensional model, if you're working on some toy model, I highly recommend it. Save yourself the time. In 2 plus 1, get ready for like some work, and in 3 plus 1, it's not there yet.
Yeah, I have a question about that. So my question about that is parallelization.
Yeah, that could help. I also parallelized it at Oregon a couple of years back, and with like MPI, I did some really naive parallelization. It helped a lot. I didn't do it in higher dimensions. I only did it in 2, but yeah, I mean, normally like the cuts are like, a normal cut value is like 40 states. That's why I kept throwing that number around. 40, 50 states when you use this. And if you can do sparse matrices and parallelize it, I got up hundreds of states. It can really help a lot, and the time can, and it's the same or faster time. So people just need to work on it. It needs, a community. I'm not trying to sell it. I'm just saying, like, if people worked on things get better. That's just normal. All right, I think I have the power to let you go, like 5 minutes early. So that's it.